Welcome everyone, and this is Fluid Mechanics. I'm Engineer Ranjan Argaming. Today we are going to discuss the concepts on stability of floating bodies. For our learning objectives, at the end of the session, you will be able to first interpret the conditions in the problems, then illustrate the free body diagrams, relate to the conditions of equilibrium to stability of floating bodies, and apply the conditions of equilibrium to evaluate the stability of floating bodies. Stability of floating bodies. So in the previous sessions, we have a floating body consists of the center of buoyancy on the submerged portion, wherein the buoyant force is concentrated to that location. We also have the center of gravity on the whole volume of the object, wherein the weight is concentrated to. A floating body is supported by a buoyant force equal to the weight of the body in which it is collinear. So this is not always the case. In many cases, weight is not always collinear with that of the buoyant force. A floating body tends to rotate where the flotation is critical when it has reached the conditions of stability. So, let us relate to the conditions of stability by having the concepts of conditions of equilibrium. So, there are three conditions of equilibrium, namely stable equilibrium, neutral equilibrium, and unstable equilibrium. Now, to explain this, first, we have stable equilibrium. Stable equilibrium, let us consider a total submerged object having this arrangement. So, this object has the heavier portion at the bottom. On the heavier portion, of course, this is where the center of gravity is nearest to. Say this is the center of gravity wherein the weight is concentrated in. And also we have the center of buoyancy. So of course, we have an upward force on that center of buoyancy, which is the buoyant force. So in here, we have a body which is in upright position. So in an upright position, we can observe that we have collinearity between the weight and the buoyant force. Now this collinearity, equal forces with collinear with each other, is actually an axiom of mechanics that satisfies equilibrium conditions. Now let us consider that this body will be tilted in a certain angle. So the configuration is the same, wherein the heavier portion is at the bottom. Just the same, there will be a center of gravity wherein the weight is concentrated in. And then we have the center of buoyancy, which is the location of the buoyant force going upwards. Now as you can see, there will be no collinearity between the center of gravity and the shifted center of buoyancy. So with this, there will be a distance between these two forces. And these two forces will go along with the same direction. So in short, because of X, there will be an equivalent righting moment or a couple. So this righting moment is actually termed as the resisting moment. By the way, this writing moment is contradicting the direction of the tilting. So the direction of the tilting is actually on a clockwise direction, while your writing moment based on the forces F, B, and W will be counterclockwise. Again, that writing moment is against the direction of the tilting, or the direction of the displacement. That is why it is called resisting moment, because it restores back the body to the original position. So it is actually the moment of stability and the moment for sustaining stability. So therefore, stable equilibriums will now be defined when a body is slightly rotated. It has the capability to restore back to its original position. Now moving on to the next condition of equilibrium, we have unstable equilibrium. So we consider again an object that is completely submerged in a liquid. So this time, the configuration is the heavier portion will be located at the top fiber. So just the same, it will have a center of buoyancy wherein we have the buoyant force and the center of gravity with the weight in it. So in this configuration, when there's no tilting, of course, again, it is satisfactory to the axioms of mechanics about the conditions of equilibrium. Two forces with the same magnitude and collinear are in equilibrium. So that is the axiom of that mechanics. So let us consider a configuration. So this configuration will be tilted, okay? So the same setup, the heavier portion will be on the top. So in here, of course, near to that heavier portion will be our center of gravity, wherein the weight is concentrated in. Just the same, it will have a center of buoyancy with the buoyant force in it. So again, notice that there will be no collinearity between the weight and the buoyant force. Hence, it will have a distance x. The distance implies a moment or rotation, since W and the buoyant force is in the same direction. This time, it is actually along the direction of the tilting. The direction of the tilting is actually clockwise, hence the overturning moment. The overturning moment OM is actually the upsetting moment because it acts along the direction of the tilting. We have also the definition of this OM as moment of instability. It is a moment force which tends to overturn the body. So therefore, the unstable equilibrium will be defined when a body is slightly rotated, it continues moving in the direction of the displaced motion. The displaced motion in the figure is clockwise. Hence, the couple formed out of the buoyant force and the weight will be also on that direction. So the last condition of equilibrium is actually as here. So just the same, it will have G and W and the center of buoyancy with the buoyant force. So basically, No matter how you tilt that one, G and BO will have the same location. So therefore, it maintains the collinearity between the weight and the buoyant force. So the weight is always collinear to the buoyant force. That is about neutral equilibrium, provided that it is a sphere of homogeneous material. So let us move on to the concept of stability. So let us consider a liquid surface, and then here an object with center of gravity and the weight. Consider the wetted portion. We have the center of buoyancy and the buoyant force going upwards. So of course we take note of this submerged draft. Okay, so this is D, which is actually the draft. So in here, we tend to tilt this object. So just the same, it will have its center of gravity with the weight in it. Notice that the wetted portion a while ago, when tilted, we have a wedge or a triangular shape here that would no longer be exposed to submerge. Okay, that will be a volume deduction from the submerged volume. Hence, that volume will be denoted by delta buoyant force. And that element of the buoyant force will be now going downwards. Why going downwards? Remember that buoyant force is going upwards, and this is a negative buoyant force since that portion is not submerged. It's no longer submerged when tilted. Now this portion a while ago was not submerged, and when tilted it's already submerged. So therefore, we'll denote that as delta FB. This time it is going upwards. So the distance between the two will be equal to L. So notice that both of these delta or additional buoyant force comes along with the same direction, and that is counterclockwise in this case. So therefore, these two additional buoyant forces would form a couple having the same direction, whether it is a righting moment or an overturning moment. So this will be equal to delta buoyant force times L. Because of this additional volume and deductive volume, of course, our BO will shift sidewise, okay, and we'll have a distance x. Now moving on, for a more detailed one, we have here the center of gravity, center of buoyancy, and again, because of that delta wedge or delta volume of the triangle, BO will shift sidewards because there will be an additional volume on that portion, and we denote that by BO prime. Okay, so BO prime will now be the new location of the buoyant force. So what we do here is to make a line that is parallel the axis of the body. So this line is along the axis of the body. And what we do is to project the new location of the buoyant force upwards, intersecting that line of symmetry. By the way, this is line of symmetry, projecting or projected along the line or the line of the body's axis, and then project this vertically upwards up to that line of symmetry. And the point of intersection will be M. Now M here is actually the metacenter. The metacenter is the point of intersection of the line of action of the body's axis and the line of action of the shifted buoyant force. So there will be an angle here formed by the two lines, and this is theta, which is actually the angle of tilt. The angle of tilt is the angle between the line formed along the axis of the body and the vertical projection of the center of gravity of the displacement, or the buoyant force. When we say displacement, take note class, that refers to the buoyant force. Now, this angle is also the angle of tilt with this angle. Okay? So we can use that angle of tilt actually on the triangle formed. Now, considering the distance between the original BO and the shifted BO, which is denoted by BO prime, say this is S, we can now perform summation moments at BO to derive some important variables here. So, of course, to maintain equilibrium, we need to equate that to 0. Positive clockwise rotation. So what would be the first term here? The buoyant force times S will be equal to delta B times L. Now, delta B times L a while ago refers to the righting or overturning moment. So we'll just have to equate that too. Now, for our buoyant force, we know that buoyant force is the gamma of the fluid times the volume submerged times S distance. Okay? In here, we refer to the delta or the additional buoyant force due to additional and deductive volume. Hence, delta FB is equal to gamma of the fluid times the volume of the wedge. Recall the wedge volume. The wedge volume is actually the volume of the triangle. Times L. So L is the distance between these two delta forces. So we can now cancel gamma of the fluid common to the sides of the equation, and then what is left will be the volume submerged times S. Now S can be calculated using this triangle here. This is a right triangle having a theta. Now, the hypotenuse of this triangle is MBO. Why MBO? Because that is the distance from M to BO. So by function of sine relating MBO, sine theta and S, sine theta opposite of theta is S and the hypotenuse is MBO, we can have that S is equal to MBO times sine of the angle of tilt. We place that in here as the value of S, equating to the volume of the wedge times L. So in here, we can now determine the distance MBO, which is equal to the wedge volume times L divided by the submerged volume times sine of theta. So by the way, MBO is the distance of metacenter to the center of buoyancy. Hence we have this formula applicable for tilted position. Why tilted position? Because in here we do have the volume of the wedge, and the volume of the wedge is the triangular portion because of the tilting. We can also say that MBO is equal to I all over the submerged volume. This is applied for an upright position, wherein I is the centroidal moment of inertia along the longitudinal section. For a rectangular parallel pip, MBO is equal to B squared all over 12D times 1 plus tangent squared of theta all over 2. So this formula is again for a tilted position. Notice that in the formula we have an angle because of the tilting. D here is the draft or the depth of flotation. Now we have here a distance from G to M, and that will be GM. Now GM is actually the metacentric height. This one. From G to M, this is GM, and GM is the metacentric height. The distance of metacenter to the center of buoyancy. A distance quantity from which the determination of stability is determined. Now, GM as a determinant of stability. Case 1. Let us have here an object tilted with G, of course. On G we have W. In here we have the shifted center of buoyancy moving sidewards. Okay. Now this will be the final location of the buoyant force when tilted. So in here we draw an axis parallel to body and then project this upwards, okay, to intersect with that line of action of the body's axis. And this is metacenter. Now, originally we have this location as our center of buoyancy. Of course, this will be the angle of tilt. So we have here a condition when M is above G. Notice that in our illustration, M is above G. When this happens, righting moment or RM prevails. And the righting moment is against the direction of the displacement. Case 2. Let us have a longer object. So in here, it has its corresponding center of gravity and the center of buoyancy. Now the center of buoyancy will be shifted to BO prime. So let us have a weight on the G, a buoyant force on the BO prime, and the line of action of the axis body of the body. So we project this upwards up to the intersect the line of action of the body. So this is actually the line of symmetry, and then the vertical projection from BO prime. So in here, the point of intersection is the metacenter. So this time, M is below G. So when this happens, overturning moment prevails. Now the overturning moment goes along the direction of the tilting. Now, the metacentric height, based on the figure from case 1, will be equal to MBO minus GBO. MBO minus GBO, based from the configuration of case 1. So in here, we can also refer to this distance. So we need that distance to get the couple. So therefore, that distance by function of sine would be equal to gm sine theta. So therefore, the writing moment will be equal to either you use the weight or the buoyant force multiplied by gm sine of theta. For case 2, we can also have this distance. Instead of having that to be equal to gm sine theta, that is mbo sine of theta. Now, gm in this case is equal to mbo plus gbo. gm is equal to mbo plus gbo. Hence, overturning moment prevails in this case. Similar formula, W or FB or the buoyant force multiplied by MBO times sine of theta. So let us have now a problem. A ship of 35.6 meganewton displacement floats in seawater with S of 1.03 with its axis of symmetry vertical when a weight of 445 kilonewton is midship. Moving the weight 3 meters towards one side of the deck causes a plumb bob suspended at the end of a string that is 4 meters long to move 25 centimeters sideways. Determine the metacentric height. So we illustrate first the liquid surface and the ship. Now the condition of 35.6 meganewton displacement, as mentioned earlier, displacement refers to buoyant force. So we place it in here as the buoyant force equal to 35,600 in kilonewton units. So the weight here is in midship. In the upright position, we have the weight here equal to 445 kilonewton. Now, this 445 kilonewton from the axis of symmetry, we are going to move that 3 meters along one side. So with that, this could imply a couple. And then the last condition in the problem is the plumb bob suspended at the side of that ship. So this plumb bob has a string of 4 meters. So when that weight is moved from the mid up to 3 meters along one side, of course, there will be tilting, and an observed sideways dimension is 0.25 meters, or that is 25 centimeters. So we will use these dimensions 4 meters and 0.25 by, or in getting the angle of tilt, theta. Because couple is equal to the weight, or FB, times gm sine of theta. Now, this couple is 445 times 3. This is equal to 35,600, which is the buoyant force, times gm times sine of theta, We do not know yet theta, but we are going to utilize the triangle formed by the plumb bob. We write tangent theta. Opposite to angle theta is 0.25. Adjacent is 4. Now we can get the angle to be equal to 3.6 degrees. So we simply substitute that into this equation. Then we can get the value of the metacentric height equal to 0.6 meters. Now moving on to the next problem, we have a scow having a rectangular section both transversely and longitudinally is 16 meter long by 10 meter wide by 4 meter deep. And floats in fresh water with a draft of 2.7 meters. If the center of gravity of the scow along its axis of symmetry at the distance of 3 meters above the bottom, determine the righting or overturning moment when the scow heeled until one end of its longitudinal side is at the point of convergence. So we have to determine whether your couple will be righting or overturning moment. So to start with, of course, we illustrate the scow in an upright position first. Of course, we take note the wetted portion. So here we have the dimension. The overall height will be 4 meters. And the width is 10 meters with the length of 16 meters. So this is the draft. According to the problem, that is 2.7 meters. Knowing that that is 2.7 meters, of course, half of that dimension is where the BO is located. And this dimension is of course half of 2.7, which is 1.35 meters. Now, the center of gravity in the problem is specified to be 3 meters above the bottom. 3 meters above the bottom. That is specified in the problem. So knowing that dimension, we can get the difference between these two. And that is actually GBO. 3 minus 1.65, that is 3 minus 1.35 will be equal to 1.65 meter, which is the GBO. So I'd like you to show the formula of MBO under upright position. So MBO is equal to I all over submerged volume. So the I for a rectangle along the longitudinal section is BH cubed all over 12. So we simply substitute. Now, you can observe here that the base here is 10 because in calculation of the center of centroidal moment of inertia under this formula is considering the centroidal moment of inertia of the longitudinal section. So the base here is just like we are going to have a view on top. Okay, so have a view on top. So when we have a view on top of this parallel pip, the base now will be 10 and the height will be 16, and that will be substituted in the formula BH cubed all over 12. Now the submerged volume is simply 2.7 or the depth of flotation times the width 10 and the length 16. So manipulating the formula, we can get MBO to be equal to 3.09 meters. Now for tilted position, we have this scow wherein one of the end is on the point of submergence. remember to put this in a way that the liquid surface would intersect the axis of symmetry at the center. We locate here the center of gravity with the weight. Now take note that this is 5 meters because we have an axis of symmetry intersecting the liquid surface. So there will be a corresponding angle here out of triangle formed. This is actually angle of tilt as mentioned earlier. And then we need this dimension, that is 4 minus the draft of 2.7, that is 1.3 meters, and become part of your right triangle here. So we can get the angle of tilt by function of tangent is equal to 1.3 all over 5. Hence theta is equal to 14.57 degrees. Moving on to the formula, MBO times volume of the wedge times L all over submerged volume times sine of theta. So performing that formula, the volume of a triangle, the additional volume is actually 1/2 times base times height, that is a triangle, 1.3 by 5, times the length, 16, to make it a volume. Now L here is 2/3 of 10. 10 is actually the width divided by the submerged volume, 2.7 by 10 by 16. Why is it that L is 2/3 of 10? Here's the explanation. In here, from this triangle formed, we get the center of gravity of that triangles. Okay, on that, we know that this distance is 1/3 of L over 2, or 1/3 of 5. And the remaining portion here, so if that is 1/3, therefore this is 2/3 of L over 2. So we add, if we multiply 2/3 of L over 2 times 2, that is 2/3 of L. So we can now have MBO to be equal to 3.19 meters. Now using the formula for a rectangular or regular parallel pip, MBO is equal to B squared all over 12D, 1 plus tangent squared theta all over 2. We have a direct substitution in it. B squared is 10 squared all over 12 times draft of 2.7 times 1 plus tangent squared 14.57 all over 2. We can calculate MBO to be equal to 3.19 meters. So in here, the metacentric height will be calculated for the calculation of our couple in a while. So the metacentric height here is MBO minus GBO. So the obtained MBO in the tilted position will be adapted. We have 3.19. We deduct 1.65 GBO that was computed a while ago. So the difference is 1.54 meters. So this will be our metacentric height. So this metacentric height is greater than 0, indicating that writing moment prevails from our assumptions. Now, writing moment is calculated by this formula, equal to the buoyant force or the weight times GM sine of theta. So in here, we need to calculate the buoyant force to complete our equation of Rm. The buoyant force is equal to gamma of the fluid times the volume displaced. The fluid gamma is 9.81 and the volume submerged is 2.7 by 10 by 16. Now this will yield to 4,237.92 kilonewton. So let me substitute that into the Rm multiplied by the Gm, 1.54 times sine of 14.57 degrees. So by this, we can calculate the writing moment to be equal to 1,642 kilonewton meter. Okay, that ends our session for today. And so long class for the next meeting. Thank you.